Hello friends. So now we are going to study the concept of entropy. What is entropy? That is very interesting topic. So first of all, I'm going to derive mathematically said that how this entropy is originated, and then after that I will explain in abstractive way that how this entropy works with respect to our daily life in practical scenario, and also with respect to the universe, why universe comes into picture while talking about the entropy. Okay, so first of all, let us try to understand its uh, original equation, that how it is developed. So let us we have a I'm going to make a graph. Okay, let us I have a PV diagram. Okay, and I am here at a point 1, that is I am here at a state 1, and I want to go to at a state 2. Let's say I have chosen a path that is called A, and that path, I have assumed that I am going with a reversible path, and then I am coming reverse to that path B, that is also a reversible path. Let's take another path C, that is also a reversible path. So here we can see that I am coming from state 1 to state 2 with a reversible path, and I have two options from returning to state 2 to 1. Okay, now if I want to apply the concept of Clausius theorem, then I can say that the closed integral of del q upon t for this whole cycle, that is from 1 to 2, is equal to 0, because the process is reversible. Now let us take the path 1, A, 2, B, 1. For this path we can write that del q upon t, which is 1a2, plus del q upon t, which is 2b1, is equal to 0, which is equation 1. Now let us write the equation for second cycle, that is 1a 2c1, which is this from 1 to 2, then 1 2 to 1 from cth path. Okay, so we can write this equation with like del q upon t from 1a2, and then del q upon t from 2c1, which is equal to 0. Let's take it as equation 2. Now if I'll subtract from 1 to equation 2, then I'll get that this value will be cancelled out, because I'm coming from state 1 to 2 with the same path in both equations, so that will be cancelled out, and I'll get with del q upon t from 2b1 minus del q upon t to c1 is equal to 0. Fine. So here we can say that del q upon t from path 2b1 is equal to del q upon t from path 2c1. It means that here I am getting that this value del q upon t is actually is not depending on the path, because for every path I am getting the same value. Just look here, I'm getting the same value. So this is actually does not depend upon the path. So this value is defined as the change of entropy. Fine. So now we can say that del q upon t for the reversible path is called the change of entropy change. Okay, so the quantity del q by t when calculated for a reversible path between two states comes out to be same irrespective of the irrespective of the reversible path followed. Hence, the quantity del Q by T irreversible must represent a change in entropy between the two states, and the property was named entropy. That's how entropy comes into the picture. Fine. Now let us, because I have shown here for the reversible path, let us try to understand for the case of the irreversible paths also. So we have a PV diagram, and I am coming from state 1 to 2 with a reversible path, that is A, and I am going with state 2 to 1 this, with path B, which is reversible. And let's say I am going from 2 to 1. Okay, let us say I'm going with the irreversible path, so it will be dotted here, because we cannot draw solid line in PV diagram. Irreversible path is always drawn with the dotted line in PV diagram. So I'm going from state 2 to state 1 with path C, which is irreversible. So now let us apply the closest concept here. So we know that for the reversible case, del Q upon T is equal to 0. That is for reversible case. So if I write for 1A, 2B, 1 cycle, we can write that del Q upon T 1A2 plus del Q upon T 2B1 is equal to 0. I can say that del Q upon T 1A2 is equal to minus del Q upon T 2B1. Let's say this is equation 1. Now, as I have explained in the previous session, that the for irreversible case, the value del Q upon T is actually less than 0. This is the closest inequality for the irreversible path. So let us try to write for this graph. I'll write that del Q upon T from 1A2 plus del Q upon T from 2C1, that is irreversible, will be less than 0. Fine. Now we can use equation 1. I am going to replace this term from equation 1. I can write it as del Q upon T from 2B1, which is minus, and this plus del Q upon T 2C1 is less than 0. Fine. So here I can say that del Q upon T 2C1 is less than del Q upon T 2B1, or we can say that because this is irreversible path, so I can say that this del Q upon T is for irreversible, which is less than del Q upon T for reversible. And we have seen that for the case of reversible, this value is actually equal to change of entropy. So we can say that del Q upon T for irreversible case is actually less than change of entropy. That's why here one more term comes into picture, that if I want to equate with change of entropy, then I have to add some extra term for the case of irreversible path, and that extra term is called actually entropy generation, and that will be equal to entropy change. So this is the equation of the second law. This is called second law equation in mathematical term. I mean second law in mathematical term, or this is also called second law. So here I can say that the entropy is a property, but entropy generation is not a property. It is path function. It is path function because it is comes out from the irreversible concept. okay. And it is not depending on the path, I mean it is the path, it depends upon the path only, because it is not equal to 0, okay. So entropic generation is a path function, that we have to keep in mind.